So we're continuing our discussion of dynamic programming. I will give a few more examples of dynamic programming and also talk about finding optimization over a DAG, which is in some sense a canonical problem for dynamic programming. And, and I want to give more examples so that you kind of get a sense of what are the kinds of substructures you need to see to spot a dynamic program. And usually, once you do a few of them, you'll start seeing the pattern that is present in most problems that can be solved through dynamic programming. Okay, so maybe let's just do a quick review of what we had last time, so that we can can motivate this discussion today. So remember that sort of the key features in a dynamic program are so I'm just going to use the discussion for knapsack. So remember that what was the 0 and knapsack problem? We have n items. Each item has an integer value and an integer weight, and we want to maximize the value of what is chosen. The constraint being that the total weight of everything we pick must be at most W. So one is, there is this recurrence that you need to construct, which is that you have a recursive feature where the problem with some particular parameters can be solved using the solutions with, quote unquote, smaller parameters, or, something that is decreasing. So you have a recursive formula, and this recursive formula is the key. Without such a recursive formula, you cannot really build the dynamic program. So you have to write this recursive formula down. When you have this recursive formula, you observe the overlapping subproblems feature, which is if you were to write out the recursion tree, many problems are actually the same in the recursion tree. And this gives the overlapping subproblems. So recursive structure plus overlapping subproblems. You can use dynamic programming, which is essentially, instead of doing it recursively, you do it bottom up. And that leads to a dynamic programming table, where typically the indices to the table are the arguments to your recursive function. You are interested in a particular cell of the dynamic of this table. So usually, let's say we keep it at the top left. And so we want the answer to the knapsack problem when the items are, I of n, which is everything, and W is the total capacity of the knapsack. And we solve this bottom up. So we solve it bottom up, and then we use the recursive formula to determine what the answer is. So we build this table. Any questions about that? Any questions about that? Right? If not, then let's, continue. And so what we'll do today is another very important problem solved by dynamic programming called longest increasing subsequence. Longest, I'll say common, which is called the LCS. LIS is also a well-known problem, which is a special case, but LCS is the longest common subsequence. So a subsequence of a string or an array is the string, or I'll say sub array obtained by taking a subset of coordinates in the same order. So for example, if you look at string, which is itself a string, the subsequences are like SG, SING, SRG, TIN, so on and so forth. This does not have to be contiguous, right? So you can take this, this, and this, and you would get sin. So on and so forth. Right? So for an n character string, there are how many subsequences? How many subsequences are there?
2 to the n.
2 to the n. Subsequences. Right? Because for each of them, you can either pick it or not. How many substrings are there? In a substring, it's usually...
choose 2.
Sorry?
And choose 2.
And choose 2. Right? Substring is they have to be contiguous. So for example, none of these are actually substrings, but STR, this is a substring because it's a contiguous portion. In a subsequence, you don't need it to be contiguous. So the LCS problem is given to strings or arrays, right? So everything that I say here is also valid for character arrays, which is basically a string. Find the length of, I'll say, a longest common subsequence. Right? Is the problem clear? So for example, if I were to take string and I were to take something like tingling, then the length of the LCS would be TING, ting. Right? In this case, it's actually a substring. And so the length is 4, and you could find the length, or you want to find a longest common subsequence. Okay, so the trivial algorithm would simply be try all subsequences. So for any subsequence, you could take a subsequence of one and check if it's a subsequence of the other. Okay, so here's a question. Given string S and string T, how long to check if T is a subsequence of S. Right, so here's S, here's T. How long does it take to check if one is a subsequence of the other? If T is a subsequence of S.
Could you do it in linear time?
Okay, linear time, how?
You just have 2 iterators, and you would, every time, so say we're comparing T to S, every time we see a character in from T in S sequentially, we would iterate forward in T, and then we would continuously iterate forward in S.
So essentially, if you think about it, I mean, I guess I haven't told you about greedy algorithms yet, but it's sort of greedy, right? So what you do is you have 2 pointers, right?
Right.
You start with this character, and you keep marching this pointer until you match this.
Right.
So that's a match. Then I move the T pointer, and then from here I keep marching on until I get a match for that. Then I draw that match.
Mm-hmm.
And so on and so forth. I keep doing this until I can match everything. Now you need a proof to argue that this is actually correct. But it's not too hard to see that if there is a subsequence, it's going to find one. Okay, so this can be done in linear time. Okay, so the trying all subsequences, this runs in time O of n times 2 to the n. I'll just say that both strings, let's say, have a length of at most n, right? So it's going to be 2 to the n. You get all subsequences of 1, and then you try to check with this procedure. So trivially, you can get an O of n times 2 to the n. That's an exponential time algorithm. And so what you want is a more efficient algorithm. Now you might ask, where does LCS used? And so if you've ever used diff, the diff utility, diff is basically computing an LCS. LCS is used heavily in genome sequencing, where you actually have the strings are DNA sequences or gene sequences, and you're trying to compare whether they both have a common ancestor or they have some commonality. And so even in a lot of analysis involving things like, looking at COVID variants and trying to understand whether one is similar to the other, usually you look at things like LCS. If the LCS is significantly different, then there have been lots of mutations. Okay? Any questions about what the problem is? Right? So what we need now is some kind of a recurrence so that we can apply dynamic programming. So the best way to think of this is, let me draw a picture here. And instead of S and T, let me use, capital. I'll use arrays A and B. So I'm going to use array notation. Okay, and so this is going from 0 to n minus 1. So let's just say that, for convenience, let's just say the length, well, actually, let's keep them, let's say one has length n and the other has length m. Okay, and let's try to come up with common subproblems. So let me give a claim over here. And this is really a very simple claim. Fix an LCS of A and B. Then one of the following must hold. So we'll think of an LCS is basically matching characters, right? So we can say who is matched to whom in an LCS. So we can say that A of n minus 1 is not part of the LCS. B of m minus 1 is not part of the LCS. Or an minus 1 is matched to bm minus 1 in the LCS. Okay, so does everyone, any questions about what this means?
So this is to say A and B do have an LCS.
Well, every two strings always have an LCS. The LCS could be empty.
Okay.
If it's empty, then of course, both 1 and 2 hold.
Would this also apply to the beginning of the arrays?
I'm sorry?
Would this also apply to the beginning of the arrays?
Yes, this would also apply to the beginning of the arrays, the first character. Good observation. So let me just prove this. I mean, the proof is actually, it just writes itself out. So suppose neither 1 nor 2 hold. So the LCS involves both a n minus 1 and b of n minus 1. Okay, let's just prove by contradiction. Now suppose a of n minus 1 is not matched to b of n minus 1. Right? So suppose a of n minus 1 is not matched to b of n minus 1. Well, because a of n minus 1 is part of the LCS, it must be matched to some b of I for I strictly less than m minus 1, right? So a of this must be matched to something here. But now you have a problem. But then b of m minus 1 cannot be matched to anything because the LCS also involves b of n minus 1. B of m minus 1 cannot be matched. B of m minus 1, cannot be matched to anything in A that completes the contradiction. It's pretty straightforward. But does everyone understand? Does everyone understand this? Right, so either a of n minus 1 is not part of the LCS, b of n minus 1 is not part of the LCS, or a of n minus 1 is matched to b of n minus 1. Now, at this point, you should have the recurrence now. So how are you going to compute the LCS of A and B with respect to LCS of subarrays? Not subsequences, but subarrays, meaning a contiguous portion of A and B. And this is what is going to give us, the polynomial time algorithm instead of it being exponential time. Yeah, any suggestions?
Are there, like, if they're both of the last ones are the same, then you can use both of them, or like it's just a maximum of like either we remove the last character from A, we remove the last character from B, or we match them if they're equal and then remove both of them.
And then remove, exactly. So the thing is, in either case, you have these three settings that I'll draw. You have A and B. So in the first case, this was case 1. So you know that A of n minus 1 is not part of the LCS. So you can basically, you just take A going from 0 to n minus 2. And you take B as before. B is going to go from 0 to n minus 1 as before. That's case 1. Picture 2, which is sort of the opposite of these. And this is 0 going to n minus 1, but B is going to be truncated. Or what you get in case 3, which is the interesting, well, part, is that these are matched to each other. And then A goes to n minus 2, B goes to m minus 2. Is this clear? So you get these 3 problems, and these problems, these are LCS problems, which are smaller. Questions? Excuse me.
So this is like the double iterator approach, just starting from the end and removing unmatched pieces one by one until you have a matched A and B match.
No, you're taking a maximum of these 3. You don't know which one to remove first. It's not a single pass. Because now if you look at this is going to generate 3 more cases. This is going to generate 3 more cases. This generates 3 more cases. If you draw out the recursion, this starts expanding out.
Oh, okay, I see.
But do you, okay, so let's now write the recurrence here, which is LCS. So I'm just going to index by the last character. I'm going to index because A and B are fixed, and I'm only changing the last position. So n minus 1 and m minus 1 is equal to the maximum of LCS of n minus 2, m minus 1, LCS of n minus 1, m minus 2, or the LCS of n minus 2, m minus 2 plus 1. I'm just going to write something here. You add this if A of n minus 1 is equal to B of m minus 1. Otherwise, you don't have this. Right? So does the recurrence make sense? So I haven't written it out as code, but you could easily write it out as code, right? You could say if these 2 characters are the same, then you have the max of these 3 things. If these characters are different, then you just take the max of these 2 because you know one of them is not going to be matched.
Shouldn't the second LCS be m minus 2?
Thank you. Yes.
Could you not have the code expressed in the if statement be the base case of LCS?
This is not the base case because when this is equal, you still have to make a recursive call. What you're making is an observation. If I'm getting correctly, you're saying that, well, if the last 2 are actually equal, you might as well match them to each other. But then have to make a recursive call here, and then you don't know which way the matches are going to happen.
Is the LCS like just getting the length of the longest?
This is only getting the length, but if you think about it, okay, so I can discuss this. It's not too hard to actually also get the actual LCS. You can pull out the LCS in the same time. So maybe let's discuss this, right? I'm just going to write things recursively, okay, and then you'll see that you'll see that this is there are actually technically you should think of there being 2 tables. Okay, so this I think of as the index of A and the last index of B. So I'll go from the last index being n minus 1 n minus 2, all the way to 0. M minus 1, M minus 2, M minus 3 to 0. What you want is this. And the base case is easy to solve. When A has just one character and B has many characters, this is easy to solve. Right? Is this clear? And so you can solve, I mean, if you want, you could even have a -1 and just put zeros over there. But you can use this formula. And so let me just write out this formula again. I'll say LCS of I and J is equal to, if AI is equal to BJ, then it's the max of LCS I minus 1J, LCS I J minus 1, or the LCS of I minus 1 J minus 1 plus 1. Else, it's just the max of LCS I minus 1J and the LCS of I J minus 1. Right? So this is going to give you the length. This is going to give you the length. How do you actually reconstruct the LIS from this?
You can do a backtrack. If from 0 and 0, 0.
Mm-hmm.
And then if you have a diagonal jump, then it's using that character. But if not, it can go horizontal or vertical. Then it is not using that. It is skipping that character.
You wouldn't go from down here because you're not entirely sure. You would probably go from the top.
Yeah. Yeah, you can go both way because at the end you will reach.
If you start from here, you have to be careful. What you do is, so let's just say that, let me write this as, what you have here is case 1, case 2, and case 3. So it's only in case 3 that you're actually found a match. It's only in case 3 that you found a match.
Could you just have LCS take strings and return a string and then compare the length by, or use max on the length of those strings returned?
You could use max on the length of the strings returned and then just, and just append this to the LIS, right? In the case 3, you have to append the last character to the LIS returned.
Right.
Right? Okay. I'm also going to draw an alternate picture here, which is very useful to keep in mind. Okay, so you're right that you can do it that way, which is, another way to do it is actually, imagine in the table, we recorded this extra piece of information. So let's just say you kept another table where what you do here is you just maintain the case. Maintain which case? Which case was the maximum? So it would say maybe this is case 2, and this would say this is case 3, and this is case 1, and 3, and 2, 1, 1, 1, 3, 2, so on and so forth. Now observe that if you're in case 2, then what you do is you decrement this, or case 2, you have to decrement the second one. So you move this way. If you're in case 3, then you record a match. Then you record a match and then you move down here. And if you're in case 1, then you move down. Case 3, you record the match. So you record the match of this and this, and then you move in this direction. So on and so forth. And if you look at this, this will take you a path that goes all the way down, which is monotonic. Does this make sense?
Yeah.
Questions about this? So what is the running time? This is n and this is m. What is the running time?
M times n.
O of m times n. And what is known? And I believe this is Masick and Patterson. I think this is the 80s, who show that you can actually get mn divided by log, like log mn. It's a big open question whether you can beat this bound. Big open question is, can you get essentially anything that is less than this? So think of it as, can you get O of n to the 2 minus delta for some delta greater than 0 where m is equal to n? Think of the both strings being the same. Can you get anything better than n squared? Right? Because this is quadratic. This is a huge open question. Some people actually believe that this is not possible. There's actually reason to believe that you cannot do this. This is believed to not be possible.
So is there a technique that can reduce the complexity?
You mean less than n squared?
Yeah, so for the log.
That's the big open question. Maybe I'm not understanding your question.
So the second one, the
Masick and Patterson?
Yeah.
Oh, what they do over here, yeah, this is sort of like a technique of it's referred to, I guess this is referred to as the four Russians trick. So what you do is you kind of actually, you break up your string into strings of size log mn, into substrings, and you almost imagine that that size of length log n is a character. And then you can actually do some sort of pre-computation on top of it, and you can do it. It's a bit more advanced, but it's not very hard. But there's sort of a standard way of removing the log n factor. In practice, this doesn't work that well. But this is like it's a well-known. I believe this is. I believe this is called like the four Russians method. Like it's sort of a standard thing where you take your string and you break it up into chunks so that in some sense you think of this entire string as one character, and then you run some sort of LCS on top of it.
Would that also increase the space complexity because you need to have an extra data structure for constructing that matching table?
No, so the thing is, oh, you mean this table? This table.
Like grouping characters.
Yeah,
together.
so what you do is you group these. Okay, so you group these into something like log n divided by 2. Right? So you group it. So imagine this is binary for simplicity. So you group it into substrings of log n divided by 2. Now you can actually enumerate over all possible such strings of that length in root n time, because 2 to the log n by 2 is root n.
Yeah.
Like log base 2n. So actually that extra space is going to be less than the space of the table itself.
Oh.
So you can do the pre-computation in such a way that the table space is actually going to be less than you're going to create a table of characters, but that table of characters and matches amongst them is actually less than the total space of the actual dynamic programming table. You have to play around with the constants.
It'll be less than m times n.
Yeah, you can even make it less than n. Forget n times n, because you could make this like something like log n divided by 4, and then when you exponentiate that, it's going to be small, and then you can pre-compute all of those matches, and you can do it. You can set up the data structure. It's not particularly hard.
Doesn't that mean you can only group repeating characters, or else you
No, no,
wouldn't.
no. You group it contiguously.
But what if two groups have overlap that could have created a substring?
That's a good point. So you have to.
Because then that
Yeah.
increases the complexity.
Yeah, but the thing is that that's a good point. So you let me see if I say this correctly. So what you can do is let me try to do this. I mean, it's a little more involved than what I'm saying here, but essentially, because you only group things of length at most log n, so you know that it's going to be some portion of this is going to get, okay, let's start with the end, right? Some portion of this is going to get matched in some way. So either it's going to be one character, or it's going to be two or three, and either they're going to be contiguous or not. Depending on various choices, you can essentially build a table. You can compress the table by a log n factor. So I'm fudging over here because you're right that, this block might match to something like that, and that's not being considered here. So you have to be a little bit more careful about doing this, but it's quite doable. It's doable. Right? So there's some offset errors that you can manage all of this usually.
It seems like in order to manage it, you would have a lot of pre-computation, which would ultimately just make it not worth it.
No, you can ensure that the pre-computation is only exponential in the size of the block. And the block size is going to be log n divided by 2. So when you exponentiate that, it's going to be small.
Okay.
So the pre-computation is exponential in the size of the block, but that's why the block is only of logarithmic size. So when you exponentiate it, it's still going to be small. Anyway, let's not go down this route, because this is in some sense this is like a more advanced technique in dynamic programming, but usually this helps you shave like log n factors off. I just want to make sure that the basic LCS makes sense. There is your recurrence, right? This is like the key. This is like the key expression that you need. All right, any questions about that? All right. Okay, so let's I want to sort of state an important let me give you another example. And I think I should be able to finish this example relatively quickly, and then I can discuss some other comments on dynamic programming. And this is called the optimal binary search tree, or BST problem. Okay, so what's the idea? The idea is that suppose you're translating a text from one language to another. And you can even think of this as think of it as mapping characters in one language to another. We might even think of it as, so every character, so let's just imagine that you have some set sigma of characters. Mapped to binary strings. Right, so there's some mapping. I'll refer to the mapping function as mu that maps characters to strings. So this means this is a string. So maybe this character is just English. You could just think of this even being ASCII. So maybe mu of A is 0, 0. Mu of B is, mu of C is 0, 1, 1, 1, so on and so forth. Okay, so now I give you a text. Now maybe you know what this text is in advance, and you basically have to do the conversion. So when you see a string, mu of string, you have to map s to something, t to something else, r to something else, so on and so forth. The question is, what is the most efficient storage of the mapping so that lookups are fast? Does that make sense? So when you see a character S, you have to go and look up which is the matching. And so you could store this in a binary search tree. So you store in a binary search tree, right? You could basically have some binary search tree. And so assume this is an ordered universe. You can basically go down and you look up mu of A here. Maybe mu of B is stored here. Mu of C is stored somewhere, whatever, right? So you have all these things stored in various places. So let's do this a little carefully. So let's just say that sigma has length n, and the BST can have depth O of log n. Each lookup can be done in O of log n. And so the translation time is equal to O of m log n, where m is the number of characters in the text. Does that make sense? Right, so you have m characters. For each of them you look up, and then you can do the translation.
Wait, so if you get an A, how do you know which direction to go?
I mean, okay,
using its index or something?
So the thing is, assume that sigma is an ordered universe.
Okay.
So A can be compared to whatever key is there, right?
Okay.
I mean, maybe this is badly written. A would probably be the leftmost path. But, right.
Sure.
Yeah. Okay. So fine. So you could just do a BST. Of course, you would need to have a balanced BST. Now, if you think about it, this might not be the most efficient solution because there may be some keys that occur more frequently, some letters that occur more frequently, like E is the most common. So you probably want to keep E near the root. And a character like Z or maybe X is so uncommon that you want to push it further down. So maybe an unbalanced binary tree is better. Okay, so now let me make this more formal. So we're given the universe sigma and a frequency vector, which I'll call f. So f basically, so f tells you how many times sigma appears. So f of little sigma is equal to the number of times sigma appears in the text. You could assume that maybe, you could compute this explicitly, or maybe this is given by historical information or whatever. Given this information, right? So the translation cost of a binary search tree is equal to the summation of the frequency of sigma times the depth of sigma, where this is the depth of sigma in the binary search tree. Does this make sense? Because when you're looking up sigma, you have to go down to that character. So maybe you have a tree that looks like this. If sigma is here, then you only need to go down one step. But sigma prime is here, then sigma prime, it's more expensive to translate, but maybe its frequency is actually much smaller. So it's fine. So you want to put the more frequent items towards the top, the less frequent items below, because you want to minimize this. And so the problem is find the BST that minimizes the translation cost. It's a pretty fundamental problem on binary search trees and algorithms. Does the question make sense? Any questions about the question?
So D can change over time, right? As we're altering our tree.
No, we will choose a fixed tree.
Okay.
So you choose a fixed translation tree.
Okay.
Think of it as I gave you a text. You know what to translate it to. So first you're going to look up the text to see, hey, which character is most frequent, and try to construct a binary search tree that's optimal for that text.
So we won't be like for example, if we find that that the frequency is high, we want to reduce the depth, we wouldn't just swap it with like a parent and then decrement D in the submission.
You've already been given the frequencies.
Right. Okay.
Does that make sense? I mean, it's so maybe this is the part that's a little unclear, and maybe I haven't phrased it well enough. You are given the universe and the frequencies. Now find the binary search tree. It's not as if you will discover the frequencies as you read the text.
Oh, okay. So it's just a one-time thing.
Yeah, think of this as a pre-processing. You've already been given the frequencies.
Okay.
Maybe you can compute the frequencies by reading the text.
Okay.
That's just a linear time thing, right? You scan through the text, get all the frequencies, because translation is more expensive than just reading through the text, say. Right? The conversion cost means that you have to do this lookup.
Right, I understand now.
I mean, okay, so I'm maybe fudging a few things here. So because technically you might argue that to actually compute the frequency vector itself requires a lookup, and so you need to build that. But let's just say maybe this is like historical. Like, for example, if you look at English text, we have a pretty good idea of frequencies of letters, which is reasonably accurate. Might not be perfect, but it's good enough. So with those frequencies, we try to find out what is the best tree. Does the question make sense?
Yeah.
I had a question. Is there a reason why a BST is used instead of something like a hash map?
Well, hash maps often, there is a space cost to using a hash table. Usually the storage cost of a hash table is much more than a binary search tree. I think even so much so that in C++, the map function is implemented as a binary search tree.
Oh, interesting.
It's actually I think it's implemented as a red-black tree.
Right.
So, hash maps, there's a lot of extra memory overhead. There's figuring out what to do if the data resizes. There's a lot of extra engineering that's required to build a good hash table. So much so that sometimes it's just better to build a self-balancing binary search tree.
And wouldn't it don't you need to have a binary search tree to like ensure that all the like I'm interpreting it as like if you go left it's a 0 and if you go right it's a 1 and every thing has like a unique ID that
No,
way?
so this is not like Huffman coding. You should think of it as basically I have some. I mean, okay, you could. It's not necessarily okay. So yes, you could interpret it in that way, that 0 is going to the left and 1 is going to the right. But I'm just saying that sort of abstractly speaking, this problem makes sense. That you just have a universe and you're trying to build a binary search tree on the universe to minimize what I'm calling the translation cost, but you can also refer to this as, instead of translation cost, you can also is the search cost. It's technically the expected search cost over this distribution. If you wanted sort of a more statistical viewpoint, it's the expected search cost according to this distribution of characters or this distribution of keys.
Okay, but how would you assign like, I guess in the original problem statement you had to assign a unique code to every.
No, so the thing is that, okay, so maybe that was, don't worry about the actual, I'm not trying to construct the map.
Okay.
I have a map and I'm storing it.
Okay.
Yeah. Yeah, we will talk about Huffman coding where you want to construct the map which is most efficient. But there you're trying to optimize the storage of the map. Here you're trying to store this map in such a way that lookups are fast.
Yeah.
So I think actually my story over here may have been misleading. So I just want to make sure that you see the formal statement of the problem as given. You're given the frequency vector, and now you just want to compute the translation cost, the search cost of the BST. So you want to minimize this quantity, which is like if I were to search for each character sigma f times, then what is the tree that's going to minimize the cost? Does that make sense? Questions?
Yeah, that does make sense. Is there kind of like a approximate value of n after which it's actually better to use a hash map, and like before that it's better to use a binary tree?
I mean, in general, the hash map versus binary search tree is not a running time, but rather a storage issue, which is sort of orthogonal to this, right? It's a question of how much storage do you need to store a binary search tree. This is now going into the constants, right? Because if you store a hash map, then you have to leave empty spaces in the hash table to make it efficient.
Yeah.
And there's a lot of engineering on how much that should be. If your tree changes, what happens? Of course, here the tree is constant. But still, in general, in many cases, the problem with a hash map is that extra storage.
Yeah.
And the engineering involved with that. Like, if you could imagine, for example, suppose that, Facebook was basically, at some point has to do a lookup depending on the queries it gets.
Mm-hmm.
And it knows that there are some people who are just much more active on Facebook.
Yeah.
So then it wants to store their information higher up in the tree, and for people who are less frequent, store it lower in the tree.
Sure.
And there you could imagine that, storage is a big issue. Like you don't want to store a hash table of things because you might end up like, with 50% more of extra just empty space to maintain the hash table.
Yeah.
So, this sort of question pops up a lot in any kind of sort of, even you could think of like content delivery or content recovery, where you could think of there being a web server and it's getting requests and it has some idea of how much, let's say, each page is being requested. So it tries to store that much closer than to store something that is less frequently observed, which is stored further on.
So what would be like the cost of a lookup once you build this like optimal BST?
This is the cost, right? The looking up sigma is the depth of sigma, because that's how far down you have to go.
Right. Okay.
And how many times do you look up sigma? F sigma. So this is the cost of all lookups of sigma, and then you're summing this over everything. So you're optimizing this quantity over all binary search trees.
Understood. Okay.
let's make life easy and let's just think of the universe being 1 to n. This is going to make life easier. Okay, so when you have a tree, there is clearly a recursive substructure. So now let's think a little aloud on how we're going to solve this problem using dynamic programming. So we first have to come up with the recurrence. So what is the first choice that you make when you have a binary search tree?
Splitting the elements somewhere.
So you have to choose the root. So choose the root. So suppose the root is I. So that means that the depth of I, I'll say this is 1 instead of 0. I'll count the number of nodes along the path. So the depth of I is 1. So you put I over there. What you put here will be the optimal BST for 1 going up to I. And this is the optimal binary search tree for I plus 1 going to n. Right? Does that make sense? So once you split there, then it makes sense to build the optimal binary search tree in each of these parts. Now we need a way to compute. We need a way to compute the cost so that we can actually run the binary search tree. So now here's the question. So let me refer to this as opt BST. This is my procedure. Opt BST. And so opt BST is some recursive procedure that's going to return the optimal. What is this total search cost? If I is the root. Okay, so firstly we have f of I times d of I. This is the cost for I. Plus, what is the cost for everything here?
The recursive call plus the number of elements.
The number of elements from 1 to I. So let me write this out as saying that this is going to be plus the opt BST for 1 through I. Right? I'm sort of abusing notation with the intervals, and we'll figure this out later on. From 1 to I, plus, because for each element over here, you're paying an extra plus 1 cost because you have to go down, plus the summation over j less than, this is I minus 1, strictly less than I of the frequency of j. So this is the cost for the left, which is 1 going into I minus 1, 1 going to I minus 1, plus the optimal BST cost for I plus 1 to n, right? Plus the summation of j strictly greater than I of the frequency of j. And this is the cost for the right side, which is I plus 1 to n. So this big expression here is the total cost. And what you want to do is you want to minimize this over all I and n. Right? So if you minimize this over all I and n, then you get your cost. Does this make sense? How many subproblems do you have?
2.
No, total. In total, how many? In total, how many subproblems? You have more than n. Think about what happens when this gets split and this gets split.
Oh, yeah. I guess it would be n choose 2.
You get a subproblem for every interval, because every time you split the interval, you get, so when you decide to split over here, maybe on some I prime, then you get a subproblem here and a subproblem here. But each of these subproblems is really just an interval. Okay, so just to be clear, I'm relaunching the poll. A is I follow, B is I'm confused.
Could you explain what that summation is for again? Like
this summation?
Yeah.
So think of it as, okay, so you're building your binary search tree by saying, suppose I put I as the root, and then I build a tree over here, and this is the optimal tree. This is the optimal tree for 1 going up to I. And this is the optimal tree for I plus 1 up to n. Sorry, this would be I minus 1. Does this make sense? This picture?
Yeah. Is the opt BST also like just like the summation at like the top of the page?
No, so the opt BST is, okay, so think of it as what's going on is you're kind of thinking about doing this through recursion, right? So what you do is you say, okay, I'm going to make a choice over here. For the left-hand side, I'm just going to use whatever recursion returns me. Recursion, suppose, gives me some optimal tree. And that optimal tree has some optimal cost. What is the optimal cost? It's exactly this. It's that summation. But this is only summed over everything going from 1 to I minus 1 in the left, and this is only summed from I plus 1 to n for everything in the right. Does that make sense?
Yeah.
Okay, but now observe that when you search for anything from 1 to I minus 1, you actually have to make one extra step to go left, because you're starting from here. You are not starting from there, the root. The optimal BST cost only takes the cost from the root. But for 1 going to I minus 1, if you solve this recursively, you get the cost of this tree. But if you search for anything from 1 to I minus 1, you have to start from the root, and you pay an extra one step. This is the extra step that you pay.
Is it 2n minus 1?
Which?
For the entire tree, the entire number of subproblems.
The number of subproblems is n squared. It's n choose 2, because you have a different subproblem for every pair, for every interval, really. You have a different subproblem for every interval. So let's get to the subproblem in a bit. First, make sure that you understand this expression, what's written in the box. Someone asked a question about this summation. Do you understand why there is that extra term there?
So would it be like just plus 1 per, like, I guess, element in the left BST?
Exactly. It's plus 1 for every element, right? Because every time you search for an element from here, in this tree, you're going to have to first start at I, you're going to go down one step, and then you're going to do whatever the optimal tree tells you down here.
Okay, I think I get it now. Thank you.
So think of it as maybe here's another way of putting it. Consider the depth of 1, say, okay? The optimal tree gives you a depth, but the depth in the full tree is whatever depth it is plus 1. The optimal tree gives you a depth, but this is the optimal tree only for 1 to I minus 1. You're building the optimal tree for everything, and so this is a subtree, and hence the depth is added with a 1 because you're coming from the root. And is this making more sense now? This is very important, so please, stop and ask me questions about this.
So for the full problem, would you have to consider every value of I for this algorithm?
You would minimize over all I, this expression. And you would solve these using recursion, and we'll see there's a dynamic programming table to be built. Questions? Yes? So this summation is because the search for any of the elements from 1 to I minus 1 has to go down to the left, which is an extra 1, plus whatever the optimal tree tells you to do. Okay, so now let me rewrite this. I'm just going to write this again. In the dynamic programming, I'll say opt BST. Now I'm going to use indices I and j. What is this? This is the optimal BST for searching elements in the interval ij. So this is just solving everything between I and j. This is going to be the minimum over all k less than I less than j. The minimum over this long expression that I'm going to write. And what is that long expression? So first I look up the time for searching the root. So this is like the root is k, and this is everything in I and k, and this is the tree, everything from k plus 1 to j. So first there's the cost of k, which is the depth of k. I'm sorry, which is just the frequency of k, because that's times 1, plus opt BST of I k minus 1, so everything in here, plus the summation of j let me not call it j, but let me call it L. L going from I less than k of the frequency of I, plus the optimal BST cost of k plus 1 to j, plus the summation of L, which is strictly greater than k, and at most j of f of L. Can you simplify this expression? What do these three things sum up to?
All of the frequencies?
In that interval. In that interval.
From I to j?
From I to j, exactly. So this is the same thing as the min of k in ij of, first I'm just going to sum all the frequencies plus the optimal BST cost from I to k minus 1, the opt BST cost k plus 1 to j. Right? This gives me my recurrence. I look at the number of subproblems I have. I have only n choose 2 subproblems to build the dynamic programming table. What is the running time of this algorithm? What is the running time?
Like n cubed.
N cubed, right? Because you have n squared subproblems. Each problem, each minimization takes O of n. Each minimization takes O of n. So O of n cube time algorithm. There are optimizations you can do. You can even get it down to n log n time, but you need sort of more observations on this. But this is sort of the key setup. So in n cube time, you can compute the optimal binary search tree. Someone asked if this is similar to the matrix multiplication problem. It is definitely related, because you do have this thing of I'm summing up the costs in one interval plus the other interval plus something. So it is very similar in structure to that. This problem can be solved in less than n cubed because there are further optimizations you can do given the structure of this problem, which is not so obvious in the matrix multiplication. But that's a good observation. This is similar in spirit to the matrix multiplication problem. There's also this notion of there is a connection between binary search trees and parentheses, that is being reflected here. But any questions about this?
I'm sorry, this may be way too from the before, but could you explain one more time? One, it's n choose 2, the number of subproblems. Yes.
Sure. Yeah. So if you look at this, there are only 2 arguments to the optimal binary search to opt BST. Each of these arguments goes from 1 to n. So it's just n squared, but technically one of the arguments is more than the second argument. So this is just an interval. At all times, you can think of this as an interval. Right? So this is just an interval from 1 to n. Like if you have all of the frequencies listed out here, you're just looking at some interval, and then you're computing opt BST for that interval, and that can be solved by computing it for subintervals. And so the number of intervals is just n choose 2. Does that answer your question?
No, I'm not sure
No?
it does. Could you, expand that a little?
So the question is, what is this? Okay, so do you understand this recurrence?
Yes. So if we're breaking a interval of length k, we have and k is a different meaning in what you've written down. But if it's length k, we have say k options of where to break it down.
Right.
And if we're starting with our n, like I'm trying to go in that direction. It doesn't make sense to me. I think you're doing something else here.
No, because the thing is, you're going top down.
Yes.
And what you're saying is, at the beginning I have n choices, and then I might have n minus 1 choice, and then n minus 2, and I start getting factorials.
Mm-hmm.
And factorials are what will happen if you run this in recursion. If you just do it recursively, that's kind of what you'll see.
Mm-hmm.
But what you notice is overlapping subproblems. The same procedure is being called again and again using recursion.
Mm-hmm.
Because what you observe is, look at the arguments of your function.
Oh, I see now.
So it's only n squared. Does that make sense now? The arguments are being repeated.
I see.
And this is the key to dynamic programming, right? The key is that the arguments are being repeated.
That was cool. Thank you.
Yeah, so I mean, it's quite neat. Like, this is the switch that you need. You when you look at it top down, you start seeing factorials and exponentials. But when you look at it bottom up, then you start seeing that, it's just the same subproblem being solved over and over again. Any questions? Okay, so I've mostly discussed all the problems on dynamic programming that I wanted to. I also wanted to mention something called the longest path of the DAG, which maybe I'll just take the last 10 minutes. I guess we have about 15 minutes, which I'll mention. An important concept or term that you should all know is something called memoization. It is not memorization. This is not a typo. There's no R. It's memoization. So it's memoization. So memoization is just a fancy term for saying that. So we talked about dynamic programs being bottom up. That's usually the way you should think about it. But we can also solve top down efficiently by storing solutions to subproblems. So let's go back to this. One approach to this would be like, okay, here's my dynamic programming table. And I'm going to sort of like solve this, then this, then this, solve it in some order. Instead, what I could do is I could just use recursion. Except every time I get a solution, store it in the table. And every time before making a recursive call, look up in the table. And it would have the same effect. But I don't need to figure out the right order. So what this means is every time a solution is obtained, store in a table. And this is called the memo. And before a recursive call, look in table to see if answer is known. Look in the table to see if the answer is already known. So you should think of memoization as more of a programming technique rather than an analysis technique. Because in some sense, these are all equivalent, whether you solve the dynamic program bottom up or top down. But memoization is just a convenient way of not having to worry about the ordering itself in the algorithm. So the algorithm just is recursive. It's just that before making this recursive call, so you first do a lookup. You first look up in the table. Does that make sense? Any questions about this? So that's what memoization does. Right, so it's nothing mysterious. It's simply saying store the output of any recursive algorithm in a table, and before you actually make a recursive call, look up in the table. That's it. Okay. I want to at this point state, sort of my last comment regarding dynamic programming, sort of in the last 10 minutes or so, which is optimization over a DAG. So consider the longest path problem on a DAG, weighted DAG. Okay, so I have some DAG. And I want to solve the longest path problem. So there are weights on this. The longest path problem can also be solved by a dynamic program. And this is in some sense not the longest path, but in general, any sort of optimization, whether it's longest path, shortest path, or various variants of it, can be solved by dynamic program. This can be solved by a dynamic program. And this is a canonical problem. What does this mean? It means that basically every dynamic program algorithm is basically optimizing over a DAG. Okay, so let's just see how would you solve the longest path problem on a DAG. So let me give you a simple recursive algorithm. So I'll say long path at V. So this is going to be the longest path starting from V. And I'm going to maximize over all vertices W, which are in the out neighborhood of V. All right, so this is V. I'm going to take the max of 1 plus, because there's one edge that I took here, plus the longest path starting on W. Right? This gives me the longest path starting from V.
Shouldn't it be the weight of the edge?
The weight of the edge. I'm sorry. You're right. The weight of VW. My apologies. Yes. So now the question is, what is the right order or right bottom-up order? For the dynamic program, right? What is the right, there's a word, there's something about it. What is the right order in which you should solve these problems?
The reverse topological order?
It's a reverse topological order. So actually this can be solved. So we can solve longest path in O of n plus n time, in linear time. But note that if I replace the max by a min, it doesn't really change. Indeed, I could replace this with any function that, I could, let's say, compute in constant time, or any function really on the neighborhood. And any function on the neighborhood itself would be enough. Now, why am I saying this? Do you see that in all the dynamic programs we have done, there's an underlying DAG and an underlying reverse topological order? Okay, I want to say this again. In every dynamic program, there is a DAG. This is the DAG of recursive calls. And this is the overlap of the subproblem. This is the overlap. When multiple programs, recursive problems, are making the same recursive call, this is the overlap. Overlap of the subproblem. So what you really are constructing when you do a dynamic program is you're basically constructing a DAG, and the DAG can be thought of as, let me show you a better picture. In this case, the DAG is quite simple. It's just all the subproblems with an edge between recursive calls. So ij points to I minus 1j, points to ij minus 1, points to I minus 1j minus 1. And what you're doing in this case is in this case, it's very similar to a longest path. You're maximizing over something with there's some weight. So you can actually think of it as you're constructing a DAG over all the problems, and you're finding a path. You're optimizing over paths in the DAG. So it's really optimizing over paths of the DAG. And this ordering that you choose is really a reverse topological ordering. The ordering of filling the table. Any questions? Am I making sense here?
Yes, sir. I have a question here.
Yeah.
So when you have a DAG, so the starting vertex would be the initial state?
Not necessarily. Like the longest path, you could think of this as the longest path starting from a place, but you could maximize over everything to just find the longest path overall, because the longest path has to start from somewhere.
And so the longest path would...
I mean, the longest path has some starting vertex.
So it can end anywhere.
It can end anywhere. This is just the longest path overall. It can end anywhere.
So the time complexity would basically be determined by the number of vertices you want. So you could,
what you do is you could imagine. Oh, sorry. So am I fudging something here? Because the minimization might not be a constant time operation. Right. Okay. So sorry, I think I made a mistake here. So because you can find the ordering in O of n plus n time, but the actual solution might actually be quadratic because you have to minimize over all of these quantities. Right. You have to basically store everything in a graph. So the minimization might actually be more expensive. So let me just say that. Okay. So let me I'll say find the ordering in n plus n time and solve in O of mn plus n squared time. Sorry. Is this clear? Does that answer your question?
Not quite. So,
okay. So what is your question?
So can you show that you can convert the optimal binary search tree problem to...
Sure. Okay, so let's look at the optimal binary search. Actually, the problem is once you see it, it's almost syntactic. Let me just pull up. Okay, so the optimal binary search tree has n squared subproblems. So create a node for every subproblem. And that has an edge to every subproblem that it might call. So ij will call all subproblems of the form ik minus 1 and k plus 1j.
So for every argument, there's a vertex, a corresponding vertex.
Yeah, for every possible recursive call, every setting of the arguments, there is a node. Does that make sense?
I have a bit of a question that might be related to this. So I am convinced that every dynamic programming problem has this kind of corresponding DAG that you can build. And finding that optimal solution, either min or max, is essentially finding the longest path of the DAG. But there is a difference in cost, right?
So yeah, you should technically think of it as, the cost in this case is not just the longest or shortest because it's more complicated.
It's also the compute of...
Because it's actually looking at two of its neighbors and then doing something with it.
Oh, okay.
So that's why I'm calling it the optimization over a DAG. It's not really the longest or shortest path. The longest and shortest are like the simplest examples of optimization. But in general, you can have any function here that looks at the neighborhood and computes something.
Oh, so the extra cost that you might have in applied dynamic programming problems comes in the fact that you sort of need to specialize for that particular condition, right?
Or rather, that is the design of the dynamic program. So you can think of the design of the dynamic program breaks up into two parts. The first part is to construct the DAG of recursive calls. And the second part is to find the right cost function.
Oh, okay. Yeah.
But it's all basically optimizing over a DAG then.
Yeah, I think that makes sense to me.
Yeah.
Thank you.
So the nice thing about this is like there's like this now nice notion of the topological order or the reverse topological order being the right order in which to solve the problems. Right? So this sort of connects the discussion that we had earlier about topological orderings and DAGs to dynamic programming. Again, that doesn't mean that when you actually solve a dynamic program in practice, you want to build the DAG explicitly. Sometimes it's not worth it. But the point is, this is like the underlying mathematics, that this is really what is going on under the hood, or this is an abstraction of what is being done.
What is the equivalency between this sort of a DAG of the dynamic programming problem and sort of like memoization, where instead of essentially navigating this DAG, you're storing kind of the results of what would be every node? Does it make sense what I'm getting?
So, the thing is, a memoization is actually related to doing a DFS on this, because that's what will happen, right? It makes a recursive call, makes a recursive call. So it's actually doing a DFS and computing. It's almost like related to finish times.
Sorry, can you repeat that last part?
It's related to finish times. Remember, how do we compute a topological order? Well, we do the topological order by looking at finish times of the DAG. If you look at what the recursive implementation does, it is also doing the same thing. It's effectively computing a topological ordering using finish times. Because every time a vertex finishes, it stores the value there.
Okay, yeah.
So it is actually very closely related to that.
Okay, yeah, I think I have to think about it more, but I think
you have to think about it a bit. Yeah, you have to think about it a bit. But if you think about what happens when a procedure finishes, that means you've finished that, so you know what the value is there.
You've calculated it.
And so therefore, you store the value, which means it's visited. And so next time you start from, let's say, this node, you don't have to visit that node again. So you're effectively doing things in topological order, reverse topological order.
Yeah, you're filling out your table essentially, right?
Exactly.
You've already visited that node, you know the cost associated.
Exactly.
Okay.
So you're implicitly computing a topological ordering because you are filling up the table in sorted order you're doing it in increasing order of reverse times, which is a reverse topological order.
Yeah, that makes sense. Yeah. Thank you.
Okay, if there are no further questions, then I will end the lecture.